Here's a quick summary of how we determine phase differences for inductors, capacitors in LRC circuits, and use phasor diagrams to analyze those circuits. If we assume a current I max times the cosine of omega t, either in an LR circuit or an LC circuit, or even in an LRC circuit or any similar circuit, any circuit involving inductors, capacitors, etc. Series circuit. Then the voltage across the inductor is just equal to the inductance times the derivative of the current, and that's very straightforward. The voltage of the capacitor is Q over C, where the current is dQ dt. To find the current function, we have to integrate the charge function. Actually, to find the charge function, we have to integrate the current function. Assuming this current function, we very easily get a function for the charge, and then the capacitance voltage is charge divided by capacitance, so we easily get an expression for the voltage across the capacitor. Simple analysis of the sine and cosine function tells us that the voltage and the current are out of phase, with the voltage preceding the current by 90 degrees of phase when the current is through an inductor, and the current preceding the voltage by 90 degrees of phase through a capacitor. From these relationships, we see that the maximum voltage on an inductor is omega L times the maximum current, and the voltage on the capacitor is 1 over omega C times the maximum current. Just follows from these equations that follow simply from these derivatives and antiderivatives. Details are actually quite straightforward. Then, of course, we have voltage equals current times resistance for a resistor. The current and the voltage are completely in phase for a resistor because the voltage is equal to the instantaneous current multiplied by the resistance. We get then these same three equations can be written as the resistor maximum voltage is the resistance times maximum current. And that's a very straightforward relationship. The voltage across the inductor, maximum voltage across the inductor, is XL times I max, the maximum current, where XL is just this omega L that we have here. This equation is the same as this equation. I've just used XL to represent omega L. And voltage, maximum voltage on the capacitor is XC times I max, just from this equation, where XC is 1 over omega C. These relationships we have here. XL, omega times L, is called the inductive reactance of the inductor. XC, the 1 over omega C for the capacitor, is called the inductive reactance for the capacitor. So here are the reactances. The capacitive reactance, the reactance of the capacitor. Again, everything follows from simple calculus on the current function and the definitions of inductance, so that the voltage is the inductance times di dt, the rate of change of the current, and capacitance Q over C, so that the charge is I max over omega times the sine of omega t, and we have this relationship then for the capacitor just using the Q over C. Very straightforward. If I of t is the current, then the voltage across the inductor is, we're doing a phasor diagram, and we should understand this because we've talked about this. So the current vector on the phasor is I of t in every case, for inductor, for capacitor, for resistor. In the case of the inductor, the voltage is 90 degrees this way, preceding the current by 90 degrees. The magnitude of the voltage depends on the inductive reactance. Magnitude of the voltage, the magnitude of the voltage vector is the maximum voltage, which in this case is omega L times I max, as we saw previously. Okay, as we reason out in the way that it was outlined just a minute ago, okay, in this same video. For the capacitor, we have 90 degrees this way. The voltage in the capacitor follows the voltage on the inductor by 90 degrees. The actual voltage and actual current are the projections on the x-axis of the current vector and the voltage vector, as you should understand at this point. And for a resistor, the voltage is in the same phase as the current, and we have the projection, the current as the projection, and the voltage across the resistor as a projection of the respective current and voltage vectors on the phasor. Depending on omega L and 1 over omega C, the voltage and the inductor voltage, the capacitor voltage will have some relative magnitude. One will generally be bigger than the other, and either one could be larger because, of course, the capacitance or the inductance can be adjusted as we wish. So in this case, I've drawn the inductance, the inductor voltage with a shorter vector than the capacitor voltage, meaning we have a greater maximum capacitor voltage than our maximum inductor voltage. These two being 180 degrees out of phase with one another, if we put everything onto the same diagram with the inductor voltage here, capacitor voltage here, and the resistance voltage here, I've just used a small resistance voltage in this case, we see that the inductor and capacitor voltage act in equal and opposite, are oriented in equal and opposite directions, so that we have the difference of the magnitude of these two vectors. That's represented by this little arrow here, and the resistor voltage here. The result of these two vectors will be down here someplace, and that's our voltage vector for the whole circuit. And that vector goes around the circle, and its projection on the horizontal axis is the actual voltage that drives the circuit. Now we can add the resistor voltage and the inductor voltage and the capacitor voltage, the expressions that we got previously, and this is our voltage function, and that function comes out like so. We just factor out the two components of the two coefficients of the sine function, and we end up with this expression omega L minus 1 over omega C. That's just the inductor reactance minus the capacitor reactance. We do a little bit of trigonometry that I'm not going to go through in detail. Just straightforward trigonometry that can be obtained without these diagrams and pictures using sum of difference of two angle formulas. We find that the maximum magnitude of the voltage in the circuit is going to be this. Okay, the square root of r squared that we get from here, and the square root of this difference squared here. They act kind of like legs of a right triangle, and here's the hypotenuse, one way to think of that. The phase angle is just going to be the arctangent of this divided by this. Again, a right triangle picture can help us see that. So that here we have a pretty complete picture of an analysis we can do on an RLC circuit without having to resort to solving differential equations. Now, it's important to be able to solve the differential equations because in certain circumstances, this analysis can fall short, especially if you, of course, you don't have an AC source. And all this, didn't say it right at the beginning, but it's written up at the top, assumes an AC current and an AC voltage.